All right, let's take a look at the questions from checkpoint number two. So first, with the same function, same graph that I gave you for checkpoint one, but now I'm going to ask some different questions about it because last week we talked about average rate of change. Now we're building that up into instantaneous rate of change. So first part of this is I want to estimate the instantaneous rate of change of this function where x equals 4. So when you're calculating average rate of change, you need 2 points and basically join those with a straight line and calculate the slope across the interval. Now, what we're essentially doing is calculating the slope at a single point, not over an interval, not over 2 points. So I'm going to try to draw a tangent line. So a line that touches this curve, in the neighborhood around that point, but only there. So here, I think I have a straight line. And again, I'm just asking for an estimate. I don't need a terribly accurate answer here, but what can I say for certain? I think I can say for certain that this has to be a positive number. At the point where x equals 4, I believe the curve is growing. It's as I look at it from left to right, my y values are getting larger. So I think I have to have a positive number. And if I look at the slope here, I don't know, it's just if I go over 2 units, I go up about 3. I think a good estimate might be 3/2. Again, your estimate it might almost certainly not be exactly 3/2. But I think what we can say is it needs to be positive and it should probably be at least 1. It looks like I have a slope that's going to be steeper than 1 there. But that's how I got my estimate. As long as you use basically, as long as your reasoning is sound, I'm happy with how you got there. Part B, find a point on the graph at which the instantaneous rate of change is equal to 0. So let's erase this annotation here. So what does it mean for an instantaneous rate of change to be 0? Well, graphically, let's think about a rate of change as a slope. So I would like to find where the slope at a single point is equal to 0. So what does it mean if a slope is 0? So slope of 0 is going to be like a horizontal line like that. So basically, I'm looking for places where the tangent line is going to be horizontal. There are a lot of options here, a lot of places where this happens. I'm going to just highlight one of them, but I'm going to go ahead and say this point here because if I look to the left of that point, the curve is kind of going downward to that point, and afterward, the curve is going upward from there. So I think because of that, I can say that that is one such point where the instantaneous rate of change is 0. I'm going to say that's x equals 3.6. Couple things to note here. If that's an estimate, you might say 3.5. Or more likely, you're probably looking at a completely different point. Like I said, there are lots of places on this graph where I think you could argue that the instant rate of change is 0. This is just one of them. Okay, so I'm going to back out a little bit because I don't need to be, that's the wrong way. I don't need to be quite this tight on this for the rest of this. C, find the average rate of change of f over the interval 3, 7. So this is something that we did last week. So I'll kind of run through this quickly. Our average rate of change, this is, at least in terms of the calculation, not much different from how you find a slope. What's f of 7 minus f of 3 divided by 7 minus 3? F of 7 looks to be, let me get rid of these annotations. F of 7 looks to be 1. And f of 3 looks to be -3. So I believe I have 4/4. So my average rate of change is 1 over this interval. All right, part D, find a point on the interval 3, 7 whose instantaneous rate of change is equal to the average rate of change. Okay, so I found the average rate of change, and I'm only looking over this interval here. So let's bookend this with some dashed lines. I would like to find a point specifically on this interval where the average rate of change is equal to 1. So what is the, or sorry, what are the instantaneous rate of change is equal to 1. So what does slope of 1 look like? It's going to look parallel to this. So I would like to find a place where my slope is, roughly the same as that. And again, I'm pushing you a little bit because we've just started talking about how to estimate the slope or the instantaneous rate of change from a graph. So I'm looking for estimates here, but maybe it's best if we start out with some counter examples. Um, if I look at what's happening at x equals 5, I think if I were to draw a tangent line here, it would be much steeper than a slope of 1. So I don't like that as an estimate. But as I move a little bit further to the right, maybe that is happening at like x equals 6. I think you could argue that as I get to x equals 6, we have a slope of about 1. So as long, again, I'm asking for estimates. I think the only part of this question where I can really demand an exact answer from you is part C. The rest of this, I am, kind of seeing how you reason through this and how you make these estimates. I'm much more interested in how you make the estimates than as to what the estimate actually is. As long as you're explaining yourself in a mathematically sound way, I'm happy with it. But it sounds like, based on what I told you, x equals 6 would be a reasonable place to make that to locate. All right, move on to part 2 or question 2 here. So a skydiver jumps out of a plane from a height of 2,500 feet. And I have given you a function that models the height of the skydiver as a function of time. And I'm asking a few questions. So part A, how far from the ground is the skydiver 5 seconds after jumping? So this question here, you don't actually need anything with rates of change, either average or instantaneous. I simply want the height. So how do I get that? Well, I told you a time, so I can use that value of time and evaluate the function there. H of 5 equals 2,500 minus 16 times 5 squared. That's equal to 2,500 minus 16 times 25. 2,500 minus 400, which is equal to 2,100 feet. So after 4 seconds, the skydiver has fallen 400 feet. So they're 2,100 feet above the ground. Part B here, what's the average speed of the skydiver over that span of time? So average rate of change, again, we're like a big part of the reason I'm asking for that here is I want you to see the difference between these two rates of change. It's not enough to say that something is a rate of change. Now I'm going to talk about what kind of rate of change it is. Is it average? Is it instantaneous? An average requires some kind of change in whatever my variable is, my independent variable. In this case, it's time. It's usually x. Whereas the instantaneous rate of change, I only care about 1 point. So how do I find the average rate of change? I want to do h of 5 minus h of 0 over 5 minus 0. So we found this h of 5, that's 2,100. What is the height at time equals 0? So if I plug in 0 for time here, I get 2,500 minus 16 times 0. So 2,100 minus 2,500 all over 5. That's equal to 400, nope, negative 400 over 5. And that is negative 80 feet per second. So why does it make sense that it's negative? Because the skydiver is falling. So their height is decreasing as time increases. So we should expect a negative value there. And finally, I want the instantaneous rate of change. So I'm not using the word rate, the phrase rate of change. I'm using speed, but a speed is a rate of change when you're talking about a function that models height or any kind of distance with a change in time. So how do I find instantaneous rates of change? That's what a derivative tells you, which is, the instantaneous rate of change of a function is one of the many ways we'll talk about what a derivative is. So I want to find the derivative of h, which we want to get used to calling that h prime. So when we name a function and say prime directly afterwards, we're saying something specific. We want to know the derivative of that function. We want to know the instantaneous rate of change of that function with respect to whatever its independent variable is. So how do I find that thing? Well, I need to involve a limit. So what's the limit here? I'm going to use any other, I'll call it b. The limit as b approaches 0 of essentially our slope calculation. I want h of 5 plus b. And I know we're used to seeing h there, but I've already used h for something else. I don't want to muddy the waters by using it, to refer to two different things. So I want the height at this time 5 plus b minus the height at time 5. So basically, I'm going to this slope calculation involves a change in my time variable. And basically b tells me how big that change is. So that's why I'm going to divide by b. And the limit's going to say, all right, I want to know what the slope is. What is this slope going to approach if I let these two x values, 5 and 5 plus b, if I let those get really, really close to each other? So if I let b get really, really small. So that's why this difference quotient, this limit definition of a derivative is what it is. It really comes from your slope calculation, which you've probably been using for years now. The big addition is this thing here, this new idea of a limit and the powerful things it can do on operations that we've been doing for quite a while. So what is h of 5 plus b? That is going to be whatever h. So now I'm evaluating a function at 5 plus b. So 2,500 minus 16 times 5 plus b squared minus h of 5, which is 2,500 minus 16 times 5 squared all over b. And we got a lot of algebraic manipulations to do here to get to the result we want. Not h goes to 0, b goes to 0. So the limit as b goes to 0 of 2,500 minus 16 times, and I'll go ahead and expand this, 5 plus b squared is equal to 25 plus 5b plus 5b, so that's plus 10b, plus b squared minus, I'm going to go ahead and drop in 2,100 here because we know, we found that in a previous part that h of 5 is 2,100. This is all over b. So as you've seen in some of the examples and probably the written or the online homework is that we would like to get to a point where I can actually evaluate this limit. Right now, I cannot let b equal 0 because I'll divide by 0, and that can't happen. So let's keep simplifying here. 16 times 25 is 400. Plus 10b, so minus 160b, minus 16b squared, minus 2,100 all over b. All right, has anything convenient happened for us yet? Hopefully you are seeing that it has. 2,500 minus 400 is 2,100. And then minus 2,100, all these constants annihilate each other. So what I'm left with is minus 160 times b minus 16b squared over b. And we're very close to a place where I can evaluate this limit because I'm going to factor out a b from the numerator. So if I factor out a b, I get negative 160 minus 16b all over b. This factor of b cancels this b. And I have the limit as b goes to 0 of Negative 160 minus 16b. So up until now, I've not been able to evaluate this limit because that would have necessitated us to divide by zero, which is not going to give us something defined. But now we're at a place where if I plug in zero for b, nothing happens to negative 160. But this negative 16b, that goes to zero. So my derivative here is negative 160. So that was a lot of algebra. Let's reflect and figure out let's remind ourselves what we just did. We found a number of 160. What is that? That is the instantaneous rate of change of the skydiver's height with respect to time at this particular time, t equals 5 seconds. So what we found is negative 160 feet per second. So average speed over this time interval was 80 feet per second downward. But we see that their speed at that exact moment, basically the end of that interval is 160 feet per second downward.